We're going to talk about inferential statistics today. So let's go ahead and get started. All right. Psychology research typically involves measuring one or more variables in a sample and computing descriptive summary data, for example, means, correlation coefficients, for those variables. These descriptive data for the sample are called statistics. The researcher's goal is not to draw conclusions about that sample, but to draw conclusions about the population that the sample was selected from. Researchers must use sample statistics to draw conclusions about the corresponding values in the population. These corresponding values in the population are called parameters. A researcher measures the number of depressive symptoms exhibited by each of 50 adults with clinical depression and computes the mean number of symptoms. The researcher probably wants to use this sample statistic, the mean number of symptoms for the sample, to draw conclusions about the corresponding population parameter, the mean number of symptoms for adults with clinical depression. Sample statistics are not perfect estimates of their corresponding population parameters. This is because there is a certain amount of random variability in any statistic from sample to sample. The mean number of depressive symptoms might be 8.73 in one sample of adults with clinical depression, 6.45 in a second sample, and 9.44 in a third, even though these samples are selected randomly from the same population. Similarly, the correlation, the Pearson's R, between two variables might be plus 0.24 in one sample, minus 0.04 in the second sample, and plus 0.15 in a third. Again, even though these samples are selected randomly from the same population. This random variability in a statistic from sample to sample is called the sampling error. Note that the term error here refers to random variability and does not imply that anyone has made a mistake. No one commits a sampling error. When there is a statistical relationship in a sample, it is not always clear that there is a statistical relationship in the population. A small difference between two group means in a sample might indicate that there is a small difference between the two group means in the population. But it could also be that there is no difference between the means in the population and that the difference in the sample is just a matter of sampling error. Similarly, a Pearson's R value of minus 0.29 in a sample might mean that there is a negative relationship in the population. But it could also be that there is no relationship in the population and that the relationship in the sample is just a matter of sampling error. In fact, any statistical relationship in a sample can be interpreted in two ways. There is a relationship in the population and the relationship in the sampling reflects this, or there is no relationship in the population and the relationship in the sample reflects only sampling error. The purpose of null hypothesis testing is simply to help researchers decide between these two interpretations. Null hypothesis testing is a formal approach to deciding between two interpretations of a statistical relationship in a sample. One interpretation is called the null hypothesis, often symbolized as HO and read as H0, H0. This is the idea that there is no relationship in the population and that the relationship in the sample reflects only sampling error. Informally, the null hypothesis is that the sample relationship occurred by chance. The other interpretation is called the alternative hypothesis, often symbolized as H1. This is the idea that there is a relationship in the population and that the relationship in the sample reflects this relationship in the population. Every statistical relationship in a sample can be interpreted as it might have occurred by chance, it might reflect a relationship in the population. Researchers need a way to decide between them. Although there are many specific null hypotheses, hypothesis testing techniques, they are all based on the same general logic. The steps are as follows. Assume for the moment that the null hypothesis is true. There is no relationship between the variables in the population. Determine how likely the sample relationship would be if the null hypothesis were true. If the sample relationship would be extremely unlikely, then reject the null hypothesis in favor of the alternative hypothesis. If it would not be extremely unlikely, then retain the null hypothesis. A crucial step in null hypothesis testing is finding the probability of the sample result or a more extreme result of the null hypothesis if the null hypothesis were true. This probability is called the p-value. A low p-value means that the sample or more extreme result would be unlikely if the null hypothesis were true and leads to the rejection of the null hypothesis. A p-value that is not low means that the sample or more extreme result would be likely if the null hypothesis were true and leads to the retention of the null hypothesis. How low must the p-value criterion be before the sample result is considered unlikely enough to reject the null hypothesis? In null hypothesis testing, this criterion is called alpha and is almost always set to 0.05. If there is a 5% chance or less of a result at least as extreme as the sample result if the null hypothesis were true, then the null hypothesis is rejected. When this happens, the result is said to be statistically significant. If there is a greater than a 5% chance of a result as extreme as the sample result when the null hypothesis is true, then the null hypothesis is retained. This does not necessarily mean that the researcher accepts the null hypothesis as true, only that there is not currently enough evidence to reject it. Researchers often use the expression fail to reject the null hypothesis rather than retain the null hypothesis, but they never use the expression accept the null hypothesis. Null hypothesis testing involves answering the question, if the null hypothesis were true, what is the probability of a sample result as extreme as this one? In other words, what is the p-value? It can be helpful to see that the answer to this question depends on just two considerations: the strength of the relationship and the size of the sample. The stronger the sample relationship and the larger the sample, the less likely the result would be if the null hypothesis were true, the lower the p-value. Imagine a study in which a sample of 500 women is compared with a sample of 500 men in terms of some psychological characteristic, and Cohen's d is a strong 0.50. If there were really no sex difference in the population, then a result this strong based on such a large sample would seem highly unlikely. Now imagine a similar study in which a sample of 3 women is compared with a sample of 3 men, and Cohen's d is a weak 0.10. If there were no sex difference in the population, then a relationship this weak based on such a small sample would seem likely. And this is precisely why the null hypothesis would be rejected in the first sample and retained in the second. Sometimes the result can be weak and the sample large, or the result can be strong and the sample small. In these cases, the two considerations trade off against each other, so that a weak result can be statistically significant if the sample is large enough, and a strong relationship can be statistically significant if the sample is small. Weak relationships based on medium or small samples are never statistically significant, and that strong relationships based on medium or larger samples are always statistically significant. If your sample relationship is strong and your sample is medium, then you should expect to reject the null hypothesis. A statistically significant result is not necessarily a strong one. Even a very weak result can be statistically significant if it is based on a large enough sample. The word significant can cause people to interpret these differences as strong and important, perhaps even important enough to influence the college courses they take or even who they vote for. However, these statistically significant differences are actually quite weak, perhaps even trivial. It is important to distinguish between the statistical significance of a result and the practical significance of that result. Practical significance refers to the importance or usefulness of the result in some real-world context. In clinical practice, this same concept is often referred to as clinical significance. For example, a study on a new treatment for social phobia might show that it produces a statistically significant positive effect. Yet this effect still might not be strong enough to justify the time, effort, and other costs of putting it into practice, especially if easier and cheaper treatments that work almost as well already exist. Although statistically significant, this result would be said to lack practical or clinical significance. Whoa, we should get inside. It's okay, lightning only kills about 45 Americans a year, so the chances of dying are only 1 in 7 million. Let's go on. The annual death rate among people who know that statistic is 1 in 6. Many studies in psychology focus on the difference between two means. The most common null hypothesis test for this type of statistical relationship is the t-test. The one-sample t-test is used to compare a sample mean with a hypothetical population mean. The formula for t is as follows. Anyway, they're supposed to be. Wait a minute. Let me get out of this. There we go. The dependent samples t-test, sometimes called the paired samples t-test, is used to compare two means for the same sample tested at two different times or under two different conditions. This comparison is appropriate for pre-test, post-test designs or within subjects' experiments. The null hypothesis is that the means of the two times or under the two conditions are the same in the population. The alternative hypothesis is that they are not the same. Independent samples t-test is used to compare the means of two separate samples. The two samples might have been tested under different conditions and between subjects' experiment, or they could be pre-existing groups in a cross-sectional design, for example, women and men, extroverts and introverts. The null hypothesis is that the means of the two populations are the same. The alternative hypothesis is that they are not the same. T-tests are used to compare two means, a sample mean with a population mean, the means of two conditions or two groups. Then when there are more than two groups or condition means to be compared, the most common null hypothesis test is the analysis of variance, or the ANOVA. The one-way ANOVA is used to compare the means of more than two samples in a between subjects design. The null hypothesis is that all the means are equal in the population. The alternative hypothesis is that not all the means in the population are equal. When we reject the null hypothesis in a one-way ANOVA, we conclude that the group means are not all the same in the population, but this can indicate different things. With three groups, it can indicate that all three means are significantly different from each other. It can indicate that one of the means is significantly different from the other two, but the other two are not significantly different from each other. Statistically significant one-way ANOVA results are typically followed up with a series of post hoc comparisons of selected pairs of group means to determine which are different from which others. A post hoc is necessary when you reject the null hypothesis that are three or more groups. No post hoc if ANOVA is NS. In general terms, they use a stricter criterion to accept an effect as significant. The simplest example is the Bonferroni method. And this is the Bonferroni method right here. But we're not going to worry about the Bonferroni method. The one-way ANOVA is appropriate for between subjects designs in which the means being compared come from separate groups of participants. It is not appropriate for within subjects designs in which the means being compared come from the same participants tested under different conditions or at different times. This requires a slightly different approach called the repeated measures ANOVA. The basics of the repeated measures ANOVA are the same as for the one-way ANOVA. The main difference is that measuring the dependent variable multiple times for each participant allows for a more refined measure of MSW. When more than one independent variable is included in a factorial design, the appropriate approach is the factorial ANOVA. The basic of the factorial ANOVA are the same as for the one-way and repeated measures ANOVAs. The main difference is that it produces an F ratio and a p-value for each main effect and for each interaction. Appropriate modifications must be made depending on whether the design is between subjects, within subjects, or mixed. For relationships between quantitative variables where Pearson's R, the correlation coefficient, is used to describe the strength of those relationships, the appropriate null hypothesis test is a test of the correlation coefficient. The basic logic is exactly the same as for other null hypothesis tests. In this case, the null hypothesis is that there is no relationship in the population. We can use the Greek lowercase rho to represent the relevant parameter. So rho equals 0. The alternative hypothesis is that there is a relationship in the population. Rho doesn't equal 0. In null hypothesis testing, the researcher tries to draw a reasonable conclusion about the population based on the sample. Unfortunately, this conclusion is not guaranteed to be correct. Rejecting the null hypothesis when it is true and retaining it when it is false are errors. Rejecting the null hypothesis when it is true is called a type 1 error. This error means that we have concluded that there is a relationship in the population when in fact there is not. Type 1 errors occur because even when there is no relationship in the population, sampling error alone will occasionally produce an extreme result. In fact, when the null hypothesis is true and alpha is 0.05, we will mistakenly reject the null hypothesis 5% of the time. This possibility is why alpha is sometimes referred to as the type 1 error rate. And of course, these are both jokes. He's telling this guy that he's pregnant. She's telling this obviously pregnant woman that she's not pregnant. And that's a type 1 error. Retaining the null hypothesis when it is false is called a type 2 error. This error means that we have concluded that there is no relationship in the population when in fact there is a relationship. Type 2 errors occur primarily because the research design lacks adequate statistical power to detect the relationship. For example, the sample is too small. Negative for COVID, but you may be pregnant. So this is a type 1 error. This is a type 1 error, and this is a type 2 error. Type 2 error is a false negative. Type 1 errors are false positives. The possibility of committing type 1 and type 2 errors is that we should be cautious about interpreting the results of any individual study because there's a chance that it reflects a type 1 or type 2 error. This possibility is why researchers consider it important to replicate their studies. Each time researchers replicate a study and find a similar result, they rightly become more confident that the result represents a real phenomenon and not just a type 1 or type 2 error. An issue related to type 1 errors is the so-called file drawer effect. The idea is that when researchers obtain statistically significant results, they tend to submit them for publication, and journal editors and reviewers tend to accept them. But when researchers obtain non-significant results, they tend not to submit them for publication. And if they do submit them, journal editors and reviewers tend not to accept them. Researchers end up putting these non-significant results away in a file drawer, or nowadays, a folder in our hard drive. And this is known as the file drawer effect. Simonson and colleagues accused psychology researchers of creating too many type 1 errors in psychology by engaging in a research practice they called p-hacking. Researchers who p-hack made various decisions in the research process to increase their chance of a statistically significant result and type 1 error. By arbitrarily removing outliers, selectively choosing to report dependent variables, only presenting significant results, etc., until their results yield a desirable p-value. Their groundbreaking paper contributed to a major conversation in the field about publishing standards and improving the reliability of our results that continues today. And of course, there's psi. The statistical power of research design is the probability of rejecting the null hypothesis given the sample size and expected relationship strength. Statistical power depends primarily on relationship strength and sample size. There are two steps you can take to increase statistical power: increase the strength of the relationship or increase the sample size. Increasing the strength of the relationship can sometimes be accomplished by using a stronger manipulation or by more carefully controlling extraneous variables to reduce the amount of noise in the data. For example, by using a within subjects design rather than a between subjects design. The usual strategy, however, is to increase the sample size. For any expected relationship strength, there will always be some sample large enough to achieve adequate power. So you just test more people. Some criticisms of null hypothesis testing focus on researchers' misunderstanding of it. We've already seen that the p-value is widely misinterpreted as the probability that the null hypothesis is true. It is really the probability of the sample result if the null hypothesis were true. A closely related misinterpretation is that 1 minus p equals the probability of replicating a statistically significant result. Another set of criticisms focuses on the logic of null hypothesis testing. To many, the strict convention of rejecting the null hypothesis when p is less than 0.05 and retaining it when p is greater then 0.05 makes little sense. I'm sorry, I got the hiccups. This criticism does not have to do with the specific value of 0.05, but with the idea that there should be any rigid dividing line between results that are considered significant and results that are not. This convention is likely to prevent good research from being published and to contribute to the file drawer problem. Yet another set of criticisms focus on the idea that null hypothesis testing, even when understood and carried out correctly, is simply not very informative. Recall that the null hypothesis is that there is no relationship between variables in the population. For example, Cohen's d or Pearson's r is precisely 0. So to reject the null hypothesis is simply to say that there is some non-zero relationship in the population. But this assertion is not really saying very much. Even those who defend null hypothesis testing recognize many of the problems with it. One suggestion is that each null hypothesis test should be accompanied by an effect size measure such as Cohen's d or Pearson's r. By doing so, the researcher provides an estimate of how strong the relationship in the population is, not just whether there is one or not. Remember that the p-value cannot substitute as a measure of relationship strength because it also depends on the sample size. Even a very weak result can be statistically significant if the sample is large enough. Another suggestion is to use confidence intervals rather than null hypothesis testing. A confidence interval around a statistic is a range of values that is computed in such a way that some percentage of the time, usually 95%, the population parameter will lie within that range. Advocates of confidence intervals argue that they are much easier to interpret than null hypothesis tests. There are more radical solutions to the problems of null hypothesis testing that involve using very different approaches to inferential statistics. Bayesian statistics is an approach in which the researcher specifies the probability that the null hypothesis and any important alternative hypothesis are true before conducting the study. Conducts the study and then updates the probabilities based on the data. It is too early to say whether this approach will become common in psychological research. For now, null hypothesis testing supported by effect size, measures, and confidence intervals remains the dominant approach. And that is it. So I had a good time. Wait a minute. Let me get out of this thing. Let's see. There we go. Okay. Yeah, this is probably it for me. I'm probably done with Diné College, mainly because they wanted me to come back to the campus, and I have a hard time living at 7,000 feet. Salie is pretty high. Right now I'm at 700 feet. I'm doing okay. Yeah, I live in Iowa, and we're not very far from the Mississippi River. We're only about 35 miles from the Mississippi River, so we're at 700 feet elevation. Salie is at 7,000 feet. It's up in the Rocky Mountains, and I have it's a minor heart condition, but it's exacerbated by elevation. I'm not really supposed to fly. Which is okay because I don't fly anyway. I don't have any place to fly to. So yeah, I'm 75 years old, so it's about time for me to retire anyway. So I enjoyed the class. I enjoy all my students. I always have. If you ever need anything, my email address is profbradway, PROFBRADWAY, at gmail.com. So I'll be glad to help you if I possibly can. Um, I don't know. That's about it. So I'll talk to you later. Or probably not.